Hey everyone, welcome to my next video. Today we're gonna continue on the topic of timers for the STM32. If you remember in the last video, we dealt with the timers, how they work, what's the logic behind them, and did a quick demo with the timers to use our first delay function. And over I have opened my template file that I have provided in my GitHub link. If you go to my GitHub account, there's a template folder inside as well. You can open it, and we have the make file and the main C file and all the other files. And here's the basic folder, the file that handles the timing, everything. So it has the USART initialized, the delay function that we have created, and the necessary GPIO and the RCC neatly packed like this, and with an example GPIO toggle bit, so your available LEDs will toggle and ascending high with the number of timer. And as you can see, I don't have the timer here because I decided for the template to have a global timer to use the system timer, and I promised to you to show you how it works. So let's go into our file, and there's a trick. So in the template file, let's just remove this and let's start. So this is the function that we used in the previous video to determine our system clocks if they were set correctly. And here I have a new line. It's system.config, system core clock divided by 1,000,000. And what this does is because in the STM32s, we also have a system timer, which is a separate one. If we go into our clock tree, we can see that exiting the AHB prescaler, here goes out the clock, and it goes through a divide by 8 over here. And it goes to the Cortex system timer. And whatever this clock is, which is obviously 180 megahertz max, and in our case it's 168 megahertz. And if we divide 168 by 8, we get neatly 21. So out of here there's 21 megahertz speed, and that is for the reference for the Cortex system timer. And we can tell this timer to which value it will count, and we do this by using this function called the system.config, and we give it the value to which we will count. So we take the system core clock that has been set up, in our case is 168 megahertz, and we divide it by 1,000,000, and in this case it will count to 1,000,000th of a second, so 1 microsecond. So what this will do is create an interrupt every microsecond. You can use divide by 1000, so just remove 3 zeros, and it will count to 1 millisecond. But we leave it at 1 microsecond, so we can have our delay microsecond and our delay millisecond. So we only just reset the global variable, the global system timer, to 0 and just wait while it reaches our desired value. Also, here is the interrupt routine. So this is the handler which gets triggered by the system timer that just increments the global variable, which is stored at the top of the code right over here. So this is our system clock configured, so we know which page we are on, and this way we don't have to use any timers per se with the libraries that I have opened right here. But today we're gonna do some more timers, so we need to use the timer libraries, and make sure to go into your make file and add it. Change your username, of course, so it will find the folders, and let's go. So I have a little video that's gonna be on top somewhere in this part of the video, where I recorded my board blinking in the beginning. So we're gonna use the toggle feature of the timer, and then you will see two lights dimming and brightening up interchangingly, and it's gonna be a bit of PWM portion, because most people want to know how to use the PWM, which is a very important feature, and it's one of the first parts of the Arduino you get learned using the analog write command. And this is all done with timers. So for the first thing, let's create a new function. I'll just copy one of those, and we're gonna call it, now it's gonna call timer, but let's just call it which timer we're gonna set up. So in order to do that, for the timer to directly affect the LEDs, we know that there's a similar connection between GPIO and the peripheral itself. And if we go to the GPIO settings, we know that if you want to use the USART, we had to connect the pin as an alternate function. So it's gonna be used by the peripheral, not by the GPIO per se. So the pin is going to be controlled directly by the peripheral. So we had to connect the RX and TX pins to the USART1 peripheral. And in this case, it's going to be the same. We need to connect the appropriate pins to the peripheral of the timer. So the timer, we have direct access to it. That way, we have to know which timer can connect to our LEDs. So if you go to our datasheet, and this is the pin mapping. So on the top of this pin mapping are all the packages. And then we need to find our LEDs, and our LEDs are on port D from 12 to 15. So if we find port D, it's going to be PD12. Oh, here it goes, PD12. It's connected to timer 4 channel 1. And they're all on timer 4 channel 2, channel 3, and channel 4. And what are those channels? Well, we already dealt with DMA, which also has channels, and maybe you can think of it the same way. Each timer counts, and if you want to do anything about what's the state of the counter in a certain position, so where in the counting process is the counter, we have the output and input compare registers. So if you go into here, and let's go back to the timers. So this is our clock tree. And if we go side panel, and if we go to our timers, and the timer 4 is one of the general purpose timers, so this is what we need to know. And if we go down the clock tree that I drew last time, here is the timer itself, and we have the compare register, the capture compare register, CCR. And this register can compare the value of the counter, that's why there's an arrow going down, to a certain value that it's been given. So it can control the output, so it has an output control, or it can be referenced to some kind of input. So the input can be sampled from a particular pin, and then filtered, prescaled, and compared to the counter state. Remember, if I open a little sketch so we can have a little fresh, so if you didn't watch the previous video, I created a little broke presentation to say, so this is our clock, so this is our clock tree in simplified. So firstly we start with the source, which is our crystal or an oscillator, and then we pass it through a selection. So it's going to be a multiplexer between the external or the internal clock or any other source, and then we have to divide it by its megahertz frequency, so we get a clean 1 megahertz output, which can be manipulated and upscaled to any number. Then we get to one of our PLL systems, which includes the PLL, which multiplies the frequency of the input followed by M and by a factor of n. And this frequency can be then divided by 3 dividers, and the first PLL that does this for the system clock only uses the divide by P, and this is going to be 2 in our case, so the output frequency that comes through the selection, again selecting from this or directly from the external clock or internal or any other clock, and this is going to be into AHB or the high-speed bus. And then this clock is gonna go in here, and then it's gonna go to the system peripherals and the system core and all of those, and then it's gonna go also to the APB. So this is the peripheral bus that we're gonna use for our timer, and then another clock goes from here that I showed before to the core clock timer as well. And when we go to the timer, so there's a frequency that comes from the APB. So this is the frequency that goes, and it goes into the prescaler. So the prescaler is a simple divider, so the clock is too high for the counter, for the values we want to count. We can use the prescaler to lower the frequency that's going into the counter. so that the counter can count to any value we want comfortably without losing the speed, or the speed we want to actually. So the counter is going to count and compare the value to the auto reload register, the ARR register, and it's going to count to the value stored in that register. And then this capture compare register that you can see in the bottom with arrows, these are going to compare the value of the counter to the value that's been set to them, and then gonna have an input or the output control. So it's gonna output something, or depending on the input it's gonna do something. So in this case we can set the capture compare register to a certain value that the counter is gonna come to. So the counter is counting to, let's say, n, which has been set by the auto reload register. Then we can say, well, let's go to some value from 0 to n. And when the counter gets to that value, that capture compare register or the capture and compare part of the peripheral gets triggered. So it's gonna output a pin high or something like that, depending on what we set in. So you can see that the fast clock with the short pulses from APB coming into the prescaler, and then it gets widened, and then we can control which part of this clock gets through. And this is also important for the PWM. So this is this little presentation. So if you go back to here, so this is a little decluttered version of this. So this is what we're gonna do. So we have 4 capture compare register. That's why we saw timer 1, or timer 4, channel 1, 2, 3, and 4. And this is exactly that. Channel 1, 2, 3, and the channel 4. So we can configure each one of these channels to trigger at a certain point of counting from the counter, and then it's gonna do something on the output. So this is all we need to know to update right now. So we know we want to use timer 4, which is our basic timer. Let's also initialize it over here, and let's create a function for it right behind the user. Okay. Before that, let's just create a clock for it, so it will run on some. So APB1 is the one that's going to it. So let's enable the APB1. So it's gonna be, it's gonna be APB1 perif clock command. It's gonna be APB1 perif clock for the timer 4. And it's gonna be enabled. So next we need to connect the GPIO, which is now controlled by the so-called software, to the GPIO of the peripheral. So let's just replace this with AF, or alternate function, and then use this command 4 times because we have 4 pins, for it to connect to GPIOD. And it's gonna be pin source 12, 13, 14, 15, and it's gonna be the timer 4. So you can look it up over here as well, but we did this a few times, so if we search this into the GPIO settings, you can find it. So we have our clock setup, we have our GPIO AF setup, so now we go straight to the function. Again, we probably have some kind of structure. So firstly, for the structure, we have this time base in it, and if we go down the timer.c and to the first, it's gonna use, we have the initialize the time, we have this type of structure. So let's initialize this structure. And let's go to one of the default settings, here it is, and just copy all of those, and we will set each one to our needs. And let's divide. Okay, so we talked about everything over here, and we can leave this all default. All we need to manipulate is these 2 values. So let's create a simple timer. So the timer is gonna blink the LEDs for a period of 2 seconds. So the LED is gonna be on for 1 second and off for 1 second. So the pulse of the timer has to be 1 second, and it's gonna be toggling. So let's create the frequency desired. So let's as you know, I still haven't figured out why it's so, but let's divide by 84 megahertz in this case, or -1, so we go to 84. So this is going to divide by 8400, and this is going to divide, if you divide the 84 megahertz by 84, we get 1 megahertz, and then divided by 100, we get 10,000 megahertz, and then we need to divide by 10,000 as well, or 9999. So it's going to be dividing by 10,000. So this is going to create 1 second pulse. As you remember, we need to have a combination between these two, so neither of those can overflow. If we added another 9 over here, this would be more than the 2 to the power of 16, because this is just a 16-bit prescaler. So we cannot just add another one here. And similarly, we cannot add another one here. So we have to have a combination of these two. So this would create a 1 second timer pulse. And now we need to initialize this as well. So time-based struct init, so this is the function that initializes it. And now we have to go up to the appropriate function. Here it is, the time-based init. This is the one that initializes everything that we have set up right now. So this is the structure that we have set up, like this. So if you don't know, we need to put the end symbol over here, because we're referencing the pointer to the structure itself. And then when this is set up, we need to define the output compare. And if you scroll the timer.h a little bit down, we have the OC init type dev, so output compare. And we're gonna use this, and we can go a little bit down as well if we find the OC. Okay, so this is the OC section, so the output compare management. So firstly, we need to define our new structure, so we're gonna copy this. It's a little bit cluttered, but if I had a bigger monitor, that would be great. But for now, this is gonna be okay. So now we need to find a function that defines the default values. Here it is. I'm gonna copy all of those into here. If for some reason, if you also want to use default values, you can just call this function in the beginning to make sure that the default values, but we're gonna override them as we want. An important thing is, if we read over here, or is it on the beginning, the M parameter, some parameters are not for all timers. So if I can show you, or maybe I'll just put a little screenshot later in the when I edit this video. But you can see these that have the N over here. This N settings can only applies to the timers 2 and 8, I believe, or 2 and 5 or something like that. The timers 2 and 5 only use this N setting, so we can remove these settings because this doesn't apply to our timer 4, which cannot use this function. So we're down to half, and now we can begin. So let's just tidy this up, and let's just pulse is the one of the most important, so let's leave it a little bit separate, and let's go to the beginning. The first is the mode. So if we search for what the modes are timing, active, inactive, toggle, and PWM 1 and 2. I won't describe what all of those are, you can read it yourself, but the most used one is the active, and the active is the simplest one. The active just says that when the timer reaches a certain value that is defined by timer pulse, and if we also copy the timer pulse and see what gets copied into it, you can see that the value of the timer pulse gets into the CCR1 register, or the capture compare register 1, which is the important part of the register, which says when the value of the timer goes to this value that is defined by time pulse, then the capture compare register will quote mark trigger it, output, or anything that it's supposed to do. So this is the most important one. So this is not a setting, this is a value. This is the ARR value equivalent over here. So the period settings over here copy into the ARR register. So this is the equivalent, so to say. So this is the one of the most important. So this one is gonna have to be set for each output separately. So the mode is active, or the next one is timing, which is a similar one, which is gonna time to this one. Inactive is gonna get it low, and the toggle is gonna toggle it. So when it's low, when it's high, it's high. PWM 1 or 2, this is basically two similar versions on PWM, just depending on when the PWM pulse is gonna start. But we're gonna use the PWM 1, which is the default one, as you can say. And this does, as you know, the PWM changes the width of the pulse depending on the value that is put in. And the short version is, I'm gonna post a picture that I just drew on the whiteboard. And in this picture you can see that the timer is gonna count to a certain value, and this value that it's gonna count, and also using the prescaler frequency, this is the frequency of the PWM itself. So the frequency of the PWM, which on Arduino is default around 500 Hz, is defined by the frequency that's coming into the peripheral that gets divided by the prescaler, and then the counter gets counted to. So if we divide in this case to 10,000, so the frequency of the counter counting is 10,000 Hz, and then the counter is gonna count to 1,000. Then this is gonna be to the value of 1 Hz. So the frequency of this PWM in this case would be 1 Hz, but if this would be left alone and the counter would only be counting to a certain value like 100, then the frequency would be 10 Hz, and so on. So it's going to be a combination of these two. So in the sketch you can see the rise time of the counter value, and then when it reaches the ARR value, when it overflows, and then the next cycle starts. So this is the whole frequency of the PWM. And then you need to have a large enough frequency and a large enough counter width so you can count very precisely. So if you have a frequency coming into the counter very high, so the counter has to count to a very high number, then the resolution of the counter is you can say it's dependent on the period over here. So in this case we count to 10,000. So the resolution is 1 Hertz in this case, because the input frequency is 10 kilohertz and we're counting 10,000 pulses, so it's 1 pulse per every millisecond. So for every pulse on the input there's a 1 increment on the counter as well. So the resolution here is 10,000, but if we would increase this number and decrease this one, so we will be counting to lower value, the frequency of the PWM will be higher, but the resolution would be smaller. That's why sometimes you would see that if you want to increase the resolution of the timer, the frequency gets lower as well. So you can't have large frequencies and large resolutions, because with large resolution you have to count to a large value, and with high frequency you need to have the prescaler very, very small, or in this case very small, so it's going on a really fast frequency, and that's harder for a faster value, because this period and prescaler aren't very large, only 16-bit or maybe 32 in some cases. So with that out of the way, we can go to others. So in this case we're gonna be toggling, because we want to toggle our LEDs, because the active one is just gonna turn them on and leave them on indefinitely unless they're being told to be shut off. So that's why you're gonna use the toggle one, so it's gonna keep switching on and off. Then it's the output state. So this is the state on the output that's gonna be presented on the output. So we want this to be enabled, so the output state will be enabled. The output state enable. So the output state will be enabled. So if this is low or disabled in this case, then the output wouldn't do anything. And then is the output polarity. So when it goes high, the output compare, then we want to enable. This is, if you would do this at low, this means when the timer would not agree, then it will enable it. So it's gonna invert the output. But let's leave it at high, which is gonna react on the counting being confirmed. So when the counter reaches a certain value, this is gonna be dependent on this pulse value. Then the output compare register will say, oh, match, and this is gonna be a high polarity. It's gonna go up. and it's gonna enable the output. And this idle state, I think that the idle state is also dependent only on 2 and 5, but just leave it there for the sake. So we just do this and say, let's say a value from 0 to, in this case the timer is gonna count to 10,000, so let's put value 1, so it's gonna, value 0. And now we need to tell, so every time the counter is gonna reach 0, the output compare would react. So now we need to set these values, which are for the output compare register, to a certain channel, because we have multiple channels. And here you can see we have timer output compare 1, output compare 2, and so on. So for each output compare part of the peripheral, we have a separate function to set it for. And we know that we have 4 LEDs, which are tied to channels from 1 to 4 to pins from 12 to 15. So if you use channel 1 and 2, we're going to be using the GPIO 12 and 13, which is going to be correspondent to channel 1 and 2. So if you use channel 1 over here, and just copy it for the channel 2 later as well, and let's just plug in the value. That's why I don't change the name of this structure, so we can just do this. It's much more simpler. And let's just leave this as timer 4 and channel 2. So this is gonna bake these settings over here into the OC timer 1. So this means in our case the LEDs 1 and 2, in this case from pin 12 to 15, I think those are green and orange in my case on this board. Then it's gonna, when the this counter comes to the value 0, this output compare is gonna trigger high, and it's gonna light up the LED. And because it's in the toggle mode, it's gonna also do it for the 0. So the next time it comes back to the 0, it's gonna disable the LEDs. And it's gonna do this for these two both. So you can save, and let's go to my terminal, and let's hit make, and that's probably the wrong file. Let's troubleshoot. Yes, I have my cheat sheet file because I always do another file. So I do this project by myself, and then when I'm satisfied with the code, I use that code as a reference to make the video code. So I was previously compiling the previous one. So let's compile this R code in this case. Let's burn it to our microcontroller. And the LED is clear. I don't have a camera right now because the thing I was using before was my phone. And for now we're gonna have to just trust and try this ourselves. So this is gonna bake this value to the output compare 1 and 2. So we have enabled all the clocks, we have enabled the GPIO over here, so this is all correct, and we have enabled our timer and the output compare. And now we can also do for different values, so we can just copy this value over here and say, let's say 5000, so this one is gonna trigger at a different value than the previous one. So I can do this as well. And it's gonna do it for a different value. So the LEDs are gonna be powering on and off at different times. So this is what this essentially is saying. So let's see what we can do. Okay, so PWM is one of the things I also said we're gonna do. And let's just create over here, and I'm just checking if everything that I said it's okay. And another thing, I just noticed why my LED wasn't blinking. Anyone notice? Well, I think I deserved an award because we haven't started the bloody counter. So the counter is not gonna start. We baked all these settings, but we haven't started the peripheral. Ah, this is a classic one. This is what we need, the timer.command. So now, hopefully, timer 4, enable. Yes. And now if we burn it, and reset the board, beep, boop, beep, boop, beep, boop, boop, boop. So it's gonna light up one LED. So this is the first one. Then it's gonna light up after a half a cycle. So the half a second. The second one, roughly, if it's counted to 10,000, and then when it's come back to 0, it's gonna disable this one and disable this one. So it's gonna be enable, enable, disable, disable, enable, enable, disable, disable. So this is the toggling does. So this is toggling. So we have confirmed the toggling, but now let's do the PWM. But in order for the PWM to have enough resolution, so it's not gonna be binary like in this case, because the frequency is only 1 Hz and that's not good for anything, we have to increase the frequency of our PWM, so these two are not gonna be visible when they're gonna count. So we only have on the one timer only one thing at a time, because this is fixed for the whole timer and the output compare are fixed to the same timer. So let's say we want a frequency of the PWM, let's say 1 kilohertz. So to do that, we have to release by 1,000. So we have to 2. So this is divided by 100 and divided by 1,000. So this is 1 kilohertz over how could you call this? So this is the 1 kilohertz reset of the timer. So the prescaler is gonna divide by the 84 megahertz, the 1 megahertz coming in, and 1 megahertz divided by 1000 is 1 kilohertz. And why did I leave it like this, not like this and this? Because now the counter would only count to 10, and yes, we would have 1 kilohertz, but what good would that be? Because we have the correct frequency, but we have no resolution. So if we increase this by 2 and decrease this by the factor of 10 to the power of 2, then we have still a higher frequency going into the counter, but the counter is going to count to a larger value. Therefore the reset value of the counter, the frequency of the reset of the counter is going to be the same, 1 kilohertz, but we have 1,000 steps. So the resolution of a counter is 1,000. So in terms of bits, what would that be? I have a calculator over here, but it's in basic mode. Is it programming? No. Advanced mode? Yes. So log power of 2. Where is it? It's not available. God damn it. That's why I have my university calculator. So if we have a log of the power of 2 of 1000, this is 2 to the roughly the power of 10. So we have roughly 10 bits of resolution on our timer, which makes sense. 2 to the power of 10 is 124. So 124. And this is 10 bits. So we could, if we increase this value, we can increase the resolution. But we had to decrease this number, so the frequency of this one would be the same. So let's say we have 1 kilohertz resolution, so 1,000 steps. So if we dim the LED 1,000 parts, this is going to be really fine. So we're gonna see, like in the video in the beginning, you could see that it's like silky smooth transition through the brightness of the LED. So we want to have this timer now in PWM mode for at least these 2 pins. So we have to change these settings for this output compare mode. Anything else can stay the same. So we have to copy this one and pulse as well. So the pulse is gonna say that when it comes to this value, stop the PWM. So it's gonna be output, so it's gonna be 0, it's gonna go high, and it's gonna be the pulse. And when it comes to this value, it's gonna go down. so it's gonna end the pulse. So this is defining the width of the pulse. So in percentage, this would be this number divided by the number that we're counting up to. So if we're counting to 1000, and this value would be half of that, so let's 500, or in this case 499, this would be a 50-50 duty cycle, because it would be on for the half of the counting time, and then it's gonna go off. So this is the PWM, and changing this value, so lowering it, this, if you have this imaginary PWM, let's say these two lines of these frames are the pulse, so the pulse is gonna go up and down. And if this is the beginning of the counting, so this is the width of the pulse, and here is the end of the period of this counting, then the width is this divided by this. And so in this case, if you want a 50-50 duty cycle, just put something like this. This would be exactly 50-50. And this would not toggle, but we want to use the PWM one, which is the default one. There's another catch though. If you look at the datasheet, you have to enable some kind of preload, which is a shadow register, and this is another register that's parallels. This is kind of waving my hands, but you can see, but the shadow register is like a secondary register that's gonna be the same as the main one that's gonna be looked into, but we only change the shadow register, which is gonna get updated to the current register on the correct clock cycle. This is kind of the way, so we don't disturb the counting by, let's say, changing the value of the register while the counter is looking into the register if it's there already. So like the ARR register also has a shadow one, I believe. So if the counter is each time looking, am I at the ARR value or not? If you would be overwriting that register, there's probably some kind of errors or internal smoke or something. So that's why we have shadow register that gets fed that new data that's gonna be implemented when it's time, when it has the time to, so it doesn't overwrite anything else. So we have to enable the shadow register in short terms. This is just something you have to do, so if you don't want to know too much about it, just don't question it and use it. So this is the function that you're gonna do. So we have the 3 and 2 now. So the 1 and 2 will be for the toggling, and the 3 and 4 are gonna be for the PWM. So you have to enable preload for the OC3 and OC4. We also want the PWM function, and then pulse. Pulse can be different. So one can pulse at 50% duty cycle, and so let's initialize our number 3. So let's just put this separately so we know which one is which. So the number 3 will have a 50% duty cycle, and if we copy this for the number 4, number 4 we have, let's say, a little lower, so 10. So it's have a 10 divided by 1000, so a 10% duty cycle. So it's gonna be very dimmer because it's gonna be, LED is gonna be on for less of a time. So let's try our luck. I'm gonna copy this and upload it, and you can upload it with this with me. And I just uploaded it, and those two LEDs that we had configured before, one is 0 because it's always reaching this number because it's doing it really fast, so it's on all the time, and the second one, we have an overflow number, so it never reaches this number. This number is perfectly fine, there's nothing wrong with it. The team pulse is gonna accept it, but this counter is never gonna get to this number, so this LED is gonna be off forever. So this is what I have a situation on my board. I'm gonna be posting the screenshot or short videos, or this can be a screenshot only. And then this LED is bright, it's not brighter than the green one, but this one is the blue LED on my board. So if you're looking at the picture right now, you know the reference to what I'm saying right now. The blue is very dim, so it's working. And maybe I'll just bring up my oscilloscope so we can have a screenshot or two on the oscilloscope as well. So all this baloney telling you that it's exactly 1 kilohertz and blah 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 is confirmed. But what if we want to change this so we can dim it? Well, we have to now use the processor, because the processor has now been not scratching his ass, but it's doing something very useless. So let's just remove this, and we're gonna define this pulse all the time. So we're gonna write to this pulse variable all the time. Now you can do this kind of thing, so you can do this, but then this TIM OC structure is only defined in this function and not in the main function. So that's a problem. So how can we go about without needing to define, again this structure and writing into it and all these settings? Well, we can just look into what register this settings is writing into. So let's go back to the pulse. No. So the pulse value is gonna be written into the CCR1 register. So we can use this command. This is some kind of low-level raw stuff. So if you use this command and just use the appropriate timer 4, this is gonna write into the CCR1 register, or in this case in the peripheral of this part. So this one is gonna be 500, and this is the same. This is the same as over here using the ocstruct.timpulse, and then this is gonna just burn this number in and using this function. So we can just use this as a raw value to directly write into this register. This is just a structure, so with this arrow it's just gonna accessing the structure. So if we use this function instead of this, we can use this into our main loop as well. So let's create a simple loop to dim the LED. So this is the one we're gonna use. So let's just use a for loop, and if you want to dim up and down, we're gonna need 2 for loops, and let's create them. So the first for loop is gonna count for, let's say, int I equals, let's say we start with 1, and it's gonna go to 1000, or in this case it's low, it's gonna go to 999, and it's gonna increment. And we're gonna write into this register the number I. So it's gonna go from 1 to 0. So the pulse is gonna be at 1 really thin, and at 999 it's gonna be the full. So the 100% duty cycle. But if you do this, it's gonna do really fast. So we have to delay this. And luckily for us, we have a delay function. So let's say delay 1 millisecond. So every 1 millisecond, this is gonna increment by 1 resolution, and so it's gonna be really silky smooth. But if we decrease this, it's gonna go faster. And then we just need to actually, what is a bother? I can just copy this and just go 900 or 1000 minus this value. So you don't need to decrease this for loop. The for loop can stay the same, but we're just gonna go reverse. So from the first number is 1, so it's gonna go from 1000 minus 1 is 999. So again, we're gonna end here on 999 and start here at 999 and go down, because this can only go down, and this is it. So this is gonna circulate. So let's save this, upload it, and let's see on my board. Come on. And it's not working. Now let's check why. Where did we go wrong? It's stationary as before. So let's just check again. Let's just upload it again. Maybe it's something wrong with the upload. And no, the LED is stationary. It's not doing anything. So let's see, where did we go wrong? Maybe this number. No, this one is correct. And delay millisecond, this one is correct as well. And yes, I was looking into it, god damn it. You're writing into the capture compare register 1, not 3 or 4. Read the manual, people. Read the manual to myself. I just upload it. Now you can see how errors get made all the time. And I'm gonna screen share this as well. I'm gonna record this later on my phone, but my LED is dimming up and down and up and down. And we can do a little trick. We can copy this over here, and let's go 1000 minus this one, and write this into the register number 4. And this way we're gonna dim them interchangeably. So while this one is getting larger, this one is getting more bright, this one is getting less bright, and a reverse here. So if we apply this, So this is gonna be the video that was played to you in the beginning. So one LED is going brighter and one is gonna get dimmer. So this is how the PWM works. So this is really simple. The video is now 45 minutes long. Good job to me for making short, informative videos. But I'm doing this very slow so you can tag along and you can understand every part of it, how it works, because it's in the end it's not that complicated if you just grasp it one time, because I think only if you understand it fully, then only then you can use it for your project or your purpose. Because if you just somebody says to you, what if I just started the video and said apply these values, and then you have to start being writing your PhD on understanding what the guy wanted to do with this code. Why is this setting like that? Why is this setting like that? Why are we writing 5000 here, and why is this is a correct value? Why are we doing this? So hopefully these long videos, if you really want to understand it, are helpful enough. So this has been the second part of the timers, and if any part leaves out, I'm gonna go and make another one. And now I'm just gonna cut to my workshop. I'm gonna use this board and gonna just take it downstairs, put it in a power bank and onto the oscilloscope so we can observe the actual waveforms on there. And so we're gonna observe how this PWM, which is the more important part. So one has, in theory, okay, 9. So this one's gonna have a 10% duty cycle. This one gonna have or this one is going to have a 0.1% duty cycle. So let's put it like 99. So this is a 10%. Sorry for everyone who's frustrated when I was saying 10% before. So this is the newest code on my board. And I'm gonna go, so let's just, and we're just gonna observe this part. So it's gonna observe this part. And thank you for watching, and see you in the next video. So yeah, now I'm at the workshop. So this is the board and here are the LEDs, and I'm probing one of those channels. I think I'm probing the PD14 with my oscilloscope probe with this wire, and I have supply of my power supply. So if I open it, and we have the waveform, and if I can focus it, so you can see how the waveform is changing from 0 to 100%. And the frequency over here on the counter is exactly 1 kilohertz. So it's going exactly from, so this period, so this is this difference over here is exactly 1 kilohertz, and you can see that it's 250 microseconds per division. So 4 divisions exactly wide is 1 millisecond, and 1 millisecond period, 1 over this is 1 kilohertz. So it's exactly like that, and it's from 0 to 513 volts roughly. So yeah, it's working. So this is the what's going on the board. So the green one is always on, the orange one is off because it has a value of 5000 that is too big for the counter, and the blue and the red one are going in and out interchangingly. So this is just the add-on. Thank you.